Hello students, welcome to EPG Pathshala. I am Gaurav Gupta from Sharda University. Today we are going to discuss about a module Inventory Control Systems Continuous Review System under paper Operations Management. Objectives. This chapter would help students to understand difference between dependent and independent demand items. Continuous review inventory control system. Concept of service level and determination of reorder point when demand is uncertain. Previous chapters on inventory management have discussed various inventory models such as economic order quantity, economic production quantity, and quantity discounts. The main purpose of these models was to identify quantity that needs to be ordered per batch so that total cost of inventory should be kept as low as possible. Total cost in these models was function of holding and ordering cost. Thus answer to question of how much to order was determined by these models under an assumption that demand of the quantity ordered would be constant. But in practice, such an assumption is rarely fulfilled. Also, these models does not answer the question of when to place an order. Under the conditions of uncertain demand, an inventory control system help in identify answer to both the questions of how much and when to place an order. The correctness of such an answer primarily depends upon understanding of nature of demand. Categorization of demand of an item into dependent or independent demand is crucial in selection of an inventory control system. Independent demand is defined as demand for items which is influenced only by market conditions and not by demand of any other item kept in stock. For instance, number of flowers a flower shop should keep would be influenced by demand for those flowers. Numbers of books of a best-selling author of a bookstore should keep in stock is influenced by market demand and not by the other book in a store. Thus, independent demand is primarily for final products or products stored at retail level. Dependent demand is for those items which are influenced by production of other items. Demand of such products is influenced by number of units stored of associated items. For instance, number of units of emblems of emblems to be used for cars produced is dependent on number of cars being manufactured. Number of tires produced is again a function of number of cars produced. For each unit of car, 4 units of tires has to be manufactured. Thus, demand of tires is dependent upon number of cars ordered. It is interesting to know that numbers of cars ordered is influenced by market forces and thus it falls into independent demand category, whereas every other item goes into producing a car falls into dependent demand category. This chapter discusses inventory control models for independent demand items. Two such models have been discussed: continuous review system called as Q system and periodic review system called as P system. Continuous review system. As the title suggests, a continuous review system tracks the inventory or remaining stock after every withdrawal. For instance, if from a stock of 50 units, first withdrawal takes 10 units and second withdrawal takes 5 units, then this system would check for remaining elements at each withdrawal of units. So after first check of stocks, the system would indicate that there is stock of 40 units, and after second check it would be indicate that stock is of 35 units. A perfect illustration of such system is cash withdrawal from ATM. After every cash withdrawal offering amount, ATM gives the receiver a receipt indicating amount of money that is stock left. It is important to note here that every cash withdrawal would not be of same amount. This can be corresponded with number of units withdrawn from inventory, which would imply the concept of application of the inventory control systems for varying demand. This system is also termed as fixed order quantity or reorder point system. FOQ implies how much to order and ROP implies when to order. According to system, tracking of stock is done whenever material is pulled out of stock. So it becomes easy to infer when stock reaches reorder point even in case of varying demand. At reorder point, an order of fixed and certain quantity of units is placed with the supplier. Continuous review queue system. Continuous review system is one of the families of stochastic models which are designed for analyzing inventory systems where there is considerable uncertainty about future demands. In this model, the inventory level is being monitored on a continuous basis so that a new order can be placed as soon as the inventory level drops to the reorder point. The traditional method of implementing a continuous review system was to use a two-bin system. All the units for a particular product would be held in two bins. The capacity of one bin would equal the reorder point. The units would first be withdrawn from the other bin. Therefore, the emptying of the second bin would trigger placing a new order. During the lead time until this order is received, units would then be withdrawn from the first bin. A continuous review inventory system for a particular product normally will be based on two critical numbers: R reorder point, Q order quantity. For a manufacturer managing its finished products inventory, the order will be for a production run of size Q. For a wholesaler or retailer or a manufacturer replenish its raw materials inventory from a supplier, the order will be purchased order for Q units of the product. An inventory policy based on these two critical numbers is a simple one. Inventory policy. Whenever the inventory level of the product drops to R units, place an order for Q more units to replenish the inventory. Each application involves a single product. The inventory level is under continuous review, so its current value always is known. An R, Q policy is to be used, so the only decisions to be made are to choose R and Q. There is a lead time between when the order is placed and when the order quantity is received. This lead time can be either fixed or variable. The demand for withdrawing units from inventory to sell them or for any other purpose during this lead time is uncertain. However, the probability distribution of demand is known or at least estimated. If a stockout occurs before the order is received, the excess demand is backlogged so that the back orders are filled once the order arrives. A fixed setup cost donated by K is incurred each time an order is placed. Except for the setup cost, the cost of the order is proportional to the order quantity Q. A certain holding cost donated by H is incurred for each unit in inventory per unit time. When a stockout occurs, a certain shortage cost denoted by P is incurred for each unit backordered per unit time until the backorder is filled. Two scenarios in Q system. As the title suggests, a continuous review system tracks the inventory or remaining stock after every withdrawal. For instance, if from a stock of 50 units, first withdrawal takes 10 units and second withdrawal takes 5 units, then this system would check for remaining elements at each withdrawal of units. So after first check of stocks, the system would indicate that there is stock of 40 units, and second check it would indicate that stock is of 35 units. This system is also termed as fixed order quantity FOQ or reorder point ROP system. FOQ implies how much to order Q and ROP implies when to order R. Estimation of Q and R has been done under two scenarios. If demand is uncertain before reorder point. As the continuous review system recommends checking of stock level after every withdrawal, so consequences of varying demand before reorder point is easily managed. If demand is high, then reorder point will be achieved earlier and next order would be placed earlier, whereas if demand is weak, then reorder point would be achieved at a later date and next order could be placed accordingly. This is easily and effectively tracked because stock is continuously checked. If demand is uncertain after reorder point, after placing an order, stock is not checked continuously till next order is made available. So question is, what should happen if demand increases or decreases at abnormal rate during the period which is after reorder level? These two cases have been discussed in following sections with illustrations. Continuous review system which with uncertain demand before reorder point. Case 1. Suppose batch size, that is Q equal to 100 units, daily demand D equal to 10 units and lead time L equal to 5 days. Lead time is the time taken by the supplier to replenish stock by Q after order has been placed. If daily demand would have been fixed at certain of 10 units, then 100 units would be consumed in 10 days, making time between order TBO to be of 10 days as shown by figure. This TBO would remain same in case of certain daily demand. Case 2. But if demand before reorder point varies in a manner that on day 1 10 units, on day 2 20 units and on day 3 20 units are consumed. This means 50 units are consumed in 3 days instead of 5 days when demand was certain. This could be tracked because of application of continuous review system as it checks remaining stock after every withdrawal. Thus, next order of 100 units is placed, that is, reorder point is achieved after 3 days. As in this illustration, demand is certain after reorder point, so remaining 50 units would be consumed at rate of 10 units per day, making TBO as 8 days as shown by figure. Case 3. In another instance, if daily demand before reorder point is weak and varies in following fashion: 5 units on day 1, 10 units on day 2, 5 units on day 3, and 10 units on day 4, 5, and 6. Each then 50 units would be consumed in 6 days as shown in table. Thus, reorder point is reached after 6 days and it is tracked from continuous review system. Next 50 units, because of constant daily demand, would be consumed in 5 days, making TBO as 11 days as shown in figure 1. Day 1 D is 10, remaining units nil. Day 2 10, remaining units 90. Day 3 D 10, remaining units 80. Likewise, day 4 remaining units 70. Day 5 remaining unit 60. Day 6 remaining unit 50. Day 7 remaining unit 40. Day 8 remaining unit 30. Day 9 remaining unit 20. Day 10 remaining unit 10. And then day 11 nil. Case 2 D10 remaining units nil. D20 remaining units 90. D20 remaining units 70. Day 4 D10 and remaining units 50. Day 5 remaining units 40. Day 6 D10 remaining units 30. Day 7 D10 remaining units 20. Day 8 D10 remaining units 10 and day 9 nil. Case 3 Day 1 D5 remaining units nil. Day 2 D10 remaining units 95. Day 3 D5 remaining units 85. Likewise, day 4 remaining units 10. Day 5 70. Day 6 60. Day 7 50. Day 8 40. Day 9 30. Day 10 20 and day 11 10. The figure shows case 1, case 2 and case 3. These three cases clearly indicates that in queue system the batch size order remains same of Q equal to 100 units. Time between order varies because of varying demand. TBO was 10 days in case 1, 8 days in case 2 and 11 days in case 3. Also, reorder point, that is time when order is placed, also varies. In case 1, order was placed after 5 days. In case 2, it was done after 3 days, and in case 3, it was placed after 6 days. In queue system, as seen from above illustrations, estimation of reorder point does not depend on varying demand before lead time, as stock level is continuously checked after every removal. Continuous review system with uncertain demand after reorder point. As shown in previous section, estimation of reorder point in queue system does not depend upon variation in demand before lead point. But what happens if demand is varying after lead time? This has been discussed by illustrating following cases. Suppose a batch size of 100 units in the stock and for first 5 days 10 units daily are consumed. Thus after 5 days a stock of 50 units is left. Now as lead time between placing and receiving an order is of 5 days, so order is placed after 5 days assuming that by the time next batch of 100 units is obtained, remaining stock of 50 units would be consumed. This makes reorder point after 5th day when 50 units are left in the stock. Case 1. Now suppose demand varies in manner such as during 6th day 10 units, during 7th and 8th day 5 units each, and during 9th and 10th day 10 units each, making a total of consumption of 40 units in next 5 days as shown in table. Thus in first 5 days daily 10 units have been consumed at constant rate, and in next 5 days a total of 40 units are consumed as shown in figure. As order has been placed after 5th day, so it would be received after 10th day operation when in stock 10 units were making total inventory of 110 units. These extra 10 units are called a safety stock. The stock at ROP level R equal to 50 minus demand during lead time L equal to 40 equal to safety stock SS equal to 10. So ROP equal to L plus SS. The table shows day during 6th day D equal to 10, remaining units 40. During 7th day D5, remaining units 35. During 8th day D5, remaining unit 30. During 9th day D10, remaining units 20. During 10th day D10, remaining units 10. Case 2, D10, remaining units 40. D20, remaining units 20. D10, remaining units 10. D10, remaining units 0. Case 2. After 5 days, when ROP is reached and stock is of 50 units, suppose demand during lead time varies in a manner such as during 6th day 10 units, during 7th day 20 units, and during 8th and 9th day 10 units each, making consumption of last 50 units in 4 days. Thus in first 5 days daily 10 units have been consumed at constant rate, and rest all 50 units are consumed in next 4 days as shown in figure. It implies that if demand during lead time is strong, then stock can get finished before replenishment. This situation is termed as out of stock. This shown in figure. These two cases clearly indicate that as it is fixed order system, so every time when ROP is reached, an order of fixed batch size Q is placed with the supplier. So if demand is weak during lead time, it would result in creation of safety stock. If demand is strong during lead time, it would result in out of stock situation and might result in loss of customers. This result in uncertainty in estimation of reorder point. In section 35.2.1, it was shown that such uncertainty in estimation of ROP was independent of variation in demand if it happens before lead time. But this uncertainty is estimation of reorder point does happen if demand varies after lead time. Resolution of this uncertainty requires understanding the concept of service level. Service level determination of safety stock. As seen in the above illustration, due to uncertainty in demand, which is a very practical scenario, an organization would always like to have safety stock to buffer against variety of demand fluctuation. But keeping a higher safety stock would incur higher holding cost, and lower safety stock would result in higher chances of losing customers. Managing this trade-off between customer service and inventory holding cost becomes a critical issue in inventory control systems. One way of determining safety stock is to set a service level which is defined as desired probability of serving the customer or not going out of stock per ordering cycle. For instance, if company operates under a service level of 95%, it would imply that during one ordering cycle, chance of demand outstripping supply is only 5%. During lead time, and company would meet customer demand 95% of the time. Higher the service level, for the instance, 99% would make company to employ systems that would result in less loss of service and reduce the level of stock out. But this would, on the other hand, would ask for keeping higher levels of safety stock, because even in cases of strong demand, company would intend to meet customer demand. However, in case of weak demand, it would result in higher stock and higher holding cost. Thus, a proper estimation of such service level becomes highly critical. To do so, have a proper understanding of variation in demand during lead time. If variability along average demand is small, then safety stock can be small. But if average demand varies greatly from one ordering cycle to other, then higher safety stock can be kept. This is gauged by recording past demand data during lead time. This data is plotted by calculating average and deviation values. This variation tends to follow normal distribution, implying the central value representing average demand. As these variations follow normal distribution, so safety stock is calculated by using following formula. Safety stock equal to Z, number of deviation deducted from Z tables, equal to standard deviation in demand during lead time. Higher service level would imply requirement of creating a higher buffer for higher variation of demand. This variation is represented by higher Z value. If Z equal to 0, there is no safety stock, meaning stock outs will occur during 50% of the order cycles. Example, records show that demand data for a product during lead time is normally distributed within. So students, let us summarize what we have learnt in this module. Inventory control systems helps to determining when the reorder and how much to order of products whose demand is independent from other products. Primarily, two inventory control systems are discussed, namely continuous review system and periodic review system. This chapter has focused on Q system, which tracks the level of stock after every withdrawal, making it convenient to judge the reorder point and when demand variation is not constant. In this system, number of units ordered per batch remains constant, whereas time between orders varies with variation in demand patterns. This concept has been illustrated in detail by taking various cases under two sections. In one section, variation in time between orders was evaluated when variation in demand is before lead time, and in other section, it was emphasized when demand variation is after lead time. Variation in demand during lead time can either result in safety stock or stock outs. To resolve these issues, concept of service level has been explained. Thank you.